Yeah, welcome back. So I next want to talk about a pretty generic approach of how you can incorporate dynamic information into a static analysis. And this can actually be useful for various reasons. So in particular, it can be used to either improve the recall of a static analyzer or to improve its precision, depending on how exactly you use the information. You can also try to do both at the same time, although that's pretty tricky. Anyway, so just a couple of years ago, we published this paper, Heaps and Leaks, and there we sought to show how heap snapshots actually improve static Android taint analysis. And I should say this is a paper that has been heavily inspired by this previous work by Neville Craig and his colleagues. So there they really showed that in pointer analysis in general, it can be very useful to actually incorporate dynamic heap snapshots into the analysis itself, so that you get a potentially better call graph, right? So in particular, they took different heap snapshots. So if you don't know this, in Java you can basically use a profiling engine that's also part of the JDK to actually create a heap snapshot for you. So that basically means you get a file dumped to disk that contains information about the pointer relationships between all the different objects in your heap. So that's normally used for debugging. But here the idea was to actually incorporate this into a static analysis. So you can basically assume that you have literally a snapshot or a picture of an entire dynamic heap of dynamically executing application. And then there are different ways of which you can incorporate this into your static analysis. So one way is, for instance, if a static analysis at a certain program point, for instance, at a at a certain reflective call site or a dynamic loading site or so, doesn't really know where certain calls are going, then maybe using a heap snapshot you get some dynamic information about certain strings and so on, so that you can actually incorporate that into your analysis, and that way you can actually improve the analysis recall, right? Because now the analysis may know about certain code locations or object relationships that it did not actually foresee statically. So you basically improve, you increase the size of your control flow graph and program supergraph, and that might just make the analysis analyze larger fractions of the program. But there's also another effect, which is you might use this dynamic information to actually restrict the static information. So you might make the explicit assumption that maybe you're not even interested in the entire static call graph that approximates or potentially executing code, but instead you want to use just a dynamic call graph, right, or dynamic pointer relationships, and not just a static pointer assignment graph. And this way you can actually shrink the scope of your analysis. You basically then obtain a static analysis that is restricted to what you actually observed in the dynamic run. And this can then use to actually boost precision. So you might lose soundness and some recall, but you might get more precise results. And actually, this was investigated in this paper, but there was also a follow-up paper here that also looked in particular into this precision point that I just discussed. Anyway, so what we looked at was how all of this can be used to actually improve not just pointer and call graph analysis, but actually also a static taint analysis on top of this, right? So we were interested in finding out, how does this impact taint analysis? Is there any impact, and if so, which one? And also, what kinds of heap snapshots should you then best collect, and at which point in time, and how should they be used in order to get the best out of this, right? And so, like I just told you, there are two different ways of using heap snapshots in general, right? So there you can augment the static information that will give you higher recall, and that was the focus of this previously published paper. But then there's also the possibility to restrict the static analysis information to gain better precision, which was part of this paper here. And we were now also asking the question, is there some middle ground? So can we use other mechanisms, in particular for taint analysis, to bring it into this corner where we actually want to go, right? To get ideally better precision and better recall. And this was really the research question that we were after here. Now, that prompted us to actually develop this approach, Heapster. So this actually uses pointer information from heap snapshots as an upper bound for a static pointer analysis, okay? And we had 3 modes of execution. So first of all, we collected separate heaps, so that really meant we would collect different heap snapshots for a running app. So in this case, we looked into Android apps. And we also analyzed, or we conducted one static analysis per snapshot, right? So that was this separate heaps configuration. But then we also had a merged heaps configuration where we had a single analysis run on a merged snapshot, so that basically merged a number of different snapshots that we had collected at different points in time over the same run of a single app. Or maybe also could also be different runs actually. Yeah, and then also we had a static fallback option, and that turned out to be very interesting. So there we would use the heap snapshots as follows. So we would use the dynamic information in general for pointer information, right? That was collected at runtime, but we might see statically some certain fields of certain classes for which no pointer information was collected, simply because these fields were not accessed during the observed run. And in this case, for these fields, we would then actually fall back to static pointer information. Okay, so if dynamic information was absent, we would use static information instead. And we implemented all of this using Suit and in this case also Flowdroid. And we then basically incorporated these dynamic heaps into the static analysis by having an extended version of the Spark pointer analysis framework. And we then had the following experimental setup. So we first of all searched for the 200 most downloaded Android apps, and we then took a sample of 49 out of them. And then first of all, we took heap snapshots after each user interaction. So we dynamically tested these apps, right? So we ran them on an emulated environment or on a phone actually, and we were interacting with these apps. And that also explains why we only looked at 49, because that was already pretty cumbersome. But then we had an approach to automatically take a heap snapshot after each such interaction, okay? Then also we took these heap snapshots, of course, and then there were 2,300 of them altogether. And we looked at these apps, but then we also came up with a real-world taint analysis benchmark. That's also part of the paper that we published, where we labeled basically some ground truths. So these are 12 real-world apps that have 157 labeled taint flows, as I should say actually as a baseline, right? So we don't know if there aren't any more interesting taint flows in these apps, but these are the ones that we found. And these are also taint flows that we know a tool such as Flowdroid should actually be able to find, just by the way it was configured, right? And So not all of these flows are positive flows. So there are about half of them that are actual flows, so that are feasible and should be found. But there are also 78 negative cases that should be infeasible. So these should not be detected by the analyzer. And we put these in there in order to be able to identify false warnings, right? False positives. And then we ran experiments using these different applications. And here I'm just showing you a brief summary of what we found. Again, there are more details in the paper, and I encourage you to take a look. So first of all, we asked the question, how are the precision and soundness impacted by using heap snapshots as an upper bound for the static analysis? Okay, and so you can see that if we only ran fully static analysis, then we would get full recall actually, right? So we had 100% recall. All the flows that should be identified, they were identified, but we only had 50% precision, right? So this was basically telling us that we had a lot of false positives here. Then when we use these dynamic heaps, you see these different configurations here. So they're actually pretty close to one another, right? So separate heaps and merged heaps in this case. But you see that the precision was dramatically improved, right? So we basically had almost no false positive, which is really kind of surprising, right? Because the dynamic information we used here is relatively coarse, right? It's only heap information. So in particular, we have no detailed information about conditionals and paths and so on, right? It's really only about points to relationships. But that really bought us a lot in terms of precision. But unfortunately, the recall also dropped dramatically, right? So we only then were able to detect fewer than 25% of the cases that needed to be detected. And that's obviously in many scenarios quite problematic. But one can say, if you are really after precision, right? So if you seek to have a highly precise tool, then maybe this can still be a useful configuration that you may actually want to run. Then we also looked into how do precision and soundness change when using the static fallback approach. And that's where I have to say this turned out to be very interesting, because when you use static fallback, we saw that you almost get the same precision gain that you also get by the other configurations. Not quite, right? But it's already a pretty dramatic precision gain. So we already are at 77% here. That's already a pretty good improvement over the 50% that we have here. And you still nonetheless get some decent recall, right? So a recall of 68%, much better than these more dynamic configurations here. So this really can be a sweet spot for many possible applications, we believe. Then the third question we looked into is how often and when should heap snapshots be collected to actually gain a useful level of precision and soundness. And so for instance, if you see that this is the app lifetime, right? So you have some time where activity 1 is active, and then maybe activity 2 is started, and then activity 3. Then we have a configuration that collects the first snapshot here, and we have a configuration that selects the last snapshot here. But we also have configurations where we basically take snapshots at all these unique activity activations here, right? And then we also have a configuration that actually regularly takes snapshots during all of these activities. And these are all different configurations that we measured, and there are many details about all of these different configurations and their combinations in the paper. Here I only want to show you the most interesting results. So we basically found that the impact is not actually that large, right? So we found that typically if you only seek to collect few heap snapshots, which can be advantageous because collecting heap snapshots itself actually takes some time at runtime. They don't come for free, so this can take several seconds depending on the app. Then it might just be a good idea to take actually a heap snapshot just at the first activity here, right? Because that already brings you a pretty long way. But we also found that if you then take further snapshots, then for the static fallback configuration, that it can actually increase both precision and recall, like you see here, but only slightly, right? So there's some improvement, but it's not huge. And for the merged heaps configuration, if you collect further information, it might also improve precision even further, depending on how you use the information. So this was actually relatively interesting to see that you could get up to 100% precision here, even in some cases. Yeah, and this I already talked about. Yeah, and like I said, so there are many more details in the paper. So in particular, we also evaluated how the heap snapshots impact the runtime performance and memory consumption of the taint analysis. You can imagine if you augment the static information, then obviously your static analysis will also run longer because just more information needs to be taken into account. And the other way around, if we restrict the static analysis using the dynamic heap, so if we restrict in particular the pointer assignment graph to a dynamic pointer assignment graph, then the analysis can actually be sped up quite a way, so it can run and terminate in a much shorter time. So just to conclude, so we have proposed in this work a static fallback mode as a new middle ground. So that actually turns out to be quite useful because it can give you a relatively precise but also soundy configuration, right? So with a pretty good recall. We put out this new benchmark, droid macro bench, which is useful to also follow up works in the space. And we investigated how heap snapshots could be incorporated into an analysis and at which points they should be gathered. And we found that if precision is critical, then a single heap snapshot can already be a very good configuration. If recall is critical, you should use the purely static or an augmented analysis, such as the static fallback mode. But the best trade-off overall really comes with static fallback, and actually here with one single snapshot per activity. That really gave us the both best out of both worlds. So here we got an F measure, so a harmonic mean between precision and recall of 77%. So that's already a pretty good number. Yeah, and so I think this is still some interesting space of work, right? So this group around Neville Gregg and Yannis Marakakis, so they were really the first to investigate this with regard to pointer analysis, and we then followed up with taint analysis here. But I'm pretty sure this general approach still has many other applications. There were also earlier papers by so-called blended analysis, where people try to incorporate different other kinds of dynamic information into static analysis or the other way around. And in general, this is a very promising approach. It's very engineering heavy, so building these kinds of tools, it's not easy. So building Heapster took a lot of time and effort, and building these tools as well, because you have to master both dynamic and static analysis. But once you do this, you can really get excellent analysis results. Yeah, that's all I wanted to teach you for this week. So thanks a lot for listening, and I'm looking forward to speaking to you again soon. Bye-bye.